So your answers to the assessment questions were by and large pretty good, but there were a few common mistakes or misconceptions just want to work through in a quick video here. Some of the questions in the assessment were quite tricky, and in particular the first question, one of the tricky parts of it was the fact that it was mixing together two different topics in one question. So it had parts of equilibrium, the topic we're currently on, and also kinetics talk before it. And a few of us find it quite tricky to separate those ideas in our head and not get them mixed up. So I'm going to go over the main ideas in those two topics just to make sure we're happy that we can tell them apart in the question. So equilibrium first, the one we've just done. Key thing to spot in an equilibrium question is you must have a reversible reaction, as shown by reversible arrows. If you've got a reversible reaction and it's in a closed system, you set up what's called an equilibrium, which has two key characteristics. It's got fixed amounts of reactants and products. Now, obviously that can change because you have questions about changing or altering the equilibrium, but those questions tend to be about an equilibrium that's already been set up and you're trying to alter it in some way. Another key feature of an equilibrium is the fact that it's not stationary, it's what we call dynamic, because both parts of the reaction are still taking place. The four inverse reactions occur at the same rate. So going back a step to the kinetics topic, there are a lot of similarities between the two topics, but there is some key differences. What we mean by kinetics is what we looked at last year, which is rates of reaction. And in terms of what rate of reaction is, it's simple enough. It's how fast the reaction goes. Now that's very simple in the case where you've got like a straightforward reaction, A going to B. The rate of the reaction is how quick you turn A into B. Maybe something you haven't thought about so much is the idea of how you describe how quick a reversible reaction is. If we've got a reversible reaction like A going to B, what we're actually talking about when we're talking about how quick that reaction is, we are talking about both parts of that reaction. We're talking about how quick the forward reaction is and also how quick the reverse reaction is. Because it's reversible, you can't just say it's one or the other because both are taking place. So in the case of a reversible reaction, we're talking about how fast forward and reverse reactions are. So if A is going to B, we're talking about how quick A is going to be and how quick B is going back to A. And if it is in equilibrium, those rates should be the same. Now, one key point is that rate and equilibrium are not the same thing and they're kind of independent of each other. What I mean by that is if you're changing a factor in a reaction, for example temperature, that might have an effect on your rate of reaction. It might also have an effect on your equilibrium position, but not necessarily the same effect and not necessarily in the same way. An example of that would be if I do something to my rate of reaction in an equilibrium or reversible reaction, it might not actually change the equilibrium at all. If I increase the rate, I'm increasing both the forward and the reverse reaction. If both reactions are speeding up by the same amount, that doesn't actually change the position of the equilibrium. So they're not always interlinked, rate and equilibrium. So to flesh that out a wee bit more, here's a little side-by-side comparison of how different factors might affect the rate in equilibrium and how they actually are different considerations to have. If I increase the concentration of something in my reaction, that will always increase the rate. Because as you remember, when you increase concentration, there's more chance of a successful collision, more chance of the rate increasing. However, with equilibrium, it's a different consideration. If I increase concentration of something, my equilibrium reaction wants to oppose that increase. So whether that's decreasing it on the reactant side or the product side, I have to look at it case by case, but it's going to do the opposite of that change I've introduced. If I increase the temperature again, that will always increase the rate of reaction, whether that's reversible or irreversible. And because it provides more energy, more particles have energy greater than the activation energy. And again with equilibrium, I'll just oppose that change. So I'll favour whichever side of the reversible reaction will cool down the reaction. So I oppose that increase. If I increase the pressure, again, back in kinetics with the fact that increasing pressure always increases the rate of reaction because the particles are closer together, the more chance of them colliding. However, if I've got an equilibrium reaction, again, I'm just going to oppose that change. In some cases, nothing might happen because you might have the same number of gas particles on each side, but the reaction is going to try to lower the pressure. Final bit a little bit different. Catalyst will always again increase rate, and it'll increase the rate of both forward and reverse reactions if it is a reversible process. However, with equilibrium, a catalyst has no effect because whilst the rate is increasing, both the forward and reverse reactions are increasing by the same amount, therefore there's no change in position of the equilibrium. So if we look at how that applied itself to the first question on the assessment, which was probably the hardest part of the assessment itself. So this question gave us a reversible process, nitrogen and oxygen reacting to make nitrogen oxide. It gave us the enthalpy change for the reaction. It's endothermic in the forward direction and exothermic in the reverse direction. Now this question, what some of us missed out, it had two parts to it. You had to explain the effect, if any, of each of the following changes on both the yield and the rate of reaction. Now rate's one thing, which a few of us missed. Yield, a few of us got confused with what that actually means. Yield in chemistry just means how much product do you make. So in other words, it's a little step beyond just describing what happens to equilibrium. It's what's happening with the equilibrium with respect to the right hand side. In other words, if I'm able to move the equilibrium to the right, that's making more product, that's increasing the yield. If I move the equilibrium to the left, that's making less product, therefore decreasing yield. So it's a slightly trickier way of asking about the equilibrium position in a question like this. So we go through each part. And the key thing once you get in your heads is the idea that rate and equilibrium, or yield, are not necessarily the same thing. You have to consider them differently. So if I increase the temperature, the first thing I look at, well, I'll just go for rate because I think it's a wee bit easier. What we said previously is that the rate of a reaction, even if it's reversible, will always increase due to temperature. So both the forward and reverse reactions will speed up, so actually we'll get the equilibrium a wee bit quicker, but the rate itself will increase. So my first point here is that the rate will increase. Now you would have to say a wee bit more than that because you have to back it up with an explanation. The reason for that is just straight out of the next topic. Particles have more energy. Therefore, there are more successful collisions. And that was your first mark. The second mark is talking about the yield, so yield's linked to the equilibrium position. If I look at my energy change for the reaction, it's endothermic in the forward direction. So if I increase the temperature, the equilibrium wants to oppose that change by decreasing the temperature. It can decrease the temperature by favouring the endothermic reaction, which is the forward one. So the implication of that is if I favour the forward reaction, I'm going to make more product, which therefore increases the yield of that product. So my points for here would be I would favour the endothermic reaction. Another way of saying that it is trying to cool itself down or opposing the temperature increase. If I favour the endothermic reaction, I could say pretty much equilibrium moves to the right. So the yield increases. I would have to mention yield in my answer because the question is about yield. The next part asks about the effect of adding more nitrogen. Effectively, it's talking about increasing the concentration of nitrogen in that reaction. So again, if I split up into rate and equilibrium or yield, rate first, what we looked at before, no matter about the equilibrium, increasing the concentration of other reactants will always speed up the reaction just by increasing the chances of a successful collision. So first little point, rate increases as you've increased the concentration of N2, therefore more chance of a successful collision. Turning to yield now, which is just about equilibrium, so remember considering it differently or separately from rate. If I've increased the concentration of nitrogen, my reaction wants to oppose that change by favouring the other side. So in order to use up nitrogen, I'm going to have to favour the right hand side of the reaction, so that's going to increase the yield of my product there. So how I put that in this case is equilibrium moves to right hand side, increasing the yield. Your justification for that would be just this removes the additional nitrogen. Part C. Now part C is one that got awfully confused in lots of cases. Remember, rate and equilibrium, consider them differently. If we look at rate first, what you've got in your connects note is that pressure will always increase the rate because you're squeezing gas particles closer together, gives them more chance to react. So first point about rate, the rate will increase as the particles are closer together. Therefore, more chance of successful collision. Considering the yield now, or the equilibrium, now it's kind of one that most of us spotted. If you look at the number of particles on the left hand side, right hand side, 2 on the left, 2 on the right, so it won't actually affect the equilibrium at all, therefore won't actually affect how much product you make at all. So you just have to justify that. One thing just in the rest of the assessment, just to point out as well, a couple of you lost marks just by not being specific enough by how you're justifying pressure changes on equilibrium. The best practice is always to actually give the number of the gas particles on each side. So in this case I would write there's 2 gas particles on the left, 2 gas particles on the right. In other parts of the assessment you have to do similar kind of explanations. So always make sure you list the number of the gas particles. So 2 gas particles on left and right. Of equilibrium. Therefore, pressure change has no effect on the equilibrium or the yield. The final one, adding a catalyst, so looking at rate first. So catalysts will always speed up the reaction. It doesn't matter that in this process speeding up both forward and reverse, that's still a reaction getting quicker. So, but we have to make sure we justify that. So rate increases because the catalyst provides a pathway of lower activation energy Then looking at the effect on yield or equilibrium, a few more of us got this. A catalyst does not affect the position of equilibrium, therefore the yield won't change. It doesn't affect that position because both forward and reverse are sped up by exactly the same amount. So catalyst has no effect